Hello everyone, and welcome back to another cartography lecture video. And in this lecture video, I want to delve deeper into this concept of distortion. And we had brought up distortion at the end of the last video when we were talking about this idea of case. And we had mentioned that with case, we had the tangent case with one point or line of tangency, that as you went away from that line, you ended up exaggerating the scale, which meant that things would be bigger or farther apart than they should be. And in the secant case, we had 2 points of contact, or 2 lines of contact in 3 dimensions, and that if you were in between those 2 lines, you actually had this compression effect, where you were actually compressing the scale, which meant that things were going to appear closer together than they would be on the reference globe. And so what I want to do now is I want to sort of build upon this idea of distortion, because we can use distortion as another method for describing map projections. And so again, we're going to be talking about this idea of distortion. And what I want to do is I want to throw out sort of 4 properties of projections, or 4 types of distortion, or 4 ways maps can be distorted. And these should probably be no surprise to you as you play around with things, as you sort of conceptually think back through the ideas of what a map projection even does. That there's going to be 4 things that we can sort of manipulate. The first is going to be the shape or the angles within the map. All right, and you can think back to that first class of map projections that we talked about with the cylindrical projections, and how they took the lines of longitude that would normally converge at the poles and spread them out so that they were parallel and perpendicular to the lines of latitude, which is not the case, right? In that case, we were very clearly changing the angles, which would change the shape. The second type of distortion we can have is a change of area, right? And we discussed this change of area when we were talking about those secant and tangent lines, when I said that you would have that expansion and compression of scale, right? You're making things look bigger or smaller, right? That's a change in area. The third way that we can have distortion, right? The third way that we can have distortion is through changes in direction. Meaning that if you were to walk along a straight line in the map, that might not necessarily correlate to a straight line in the real world. And then finally, we can distort distance. And this one you have to be careful with, because a lot of times when we try to make measurements on maps, we're assuming that the map projection is not distorting distances. So when you're trying to make real-world measurements, it's important to make sure that you have a good understanding of the underlying map projection so that your distance measurements are as accurate as possible. Now, the nice thing about cartography is that we don't necessarily have to worry too much about the underlying mathematics to be able to sort of create some key terminology that will allow us to both explain distortion, visualize distortion, and also be able to use some key terms to pick out map projections that will allow us to address these 4 types of distortion. Because again, right, depending on the use of the map, these different types of distortion may be more important or less important, right? If you're trying to measure the area of a landmass, you really are going to want to focus in on trying to address area distortion, but you might not care as much about direction. Versus if you're trying to make a map that is highlighting the shapes of coastlines or something, you would want to focus a lot more on this idea of shape and angles rather than area, for example. So let's go ahead and parlay this idea of the 4 types of distortion into being able to talk about how we can actually visualize or explain or quantify distortion. Right? Or put another way, how do we measure distortion? And there's two ways that we can do this. The first is numerically. And the way we do this is with what's called a scale factor. And essentially what a scale factor is it's a ratio between the measured scale of the map compared to what we were intending it to be with the reference globe. So essentially it's a ratio of measured scale to expected scale. A ratio of measured scale to expected scale. And what I mean by that is when we began this whole process, we picked a reference globe, and that reference globe was built at a specific size relationship to the Earth. And then we mentioned when we did the aspect in case that we could manipulate that and those lines of tangents and secant lines so that we would have distortion as we went away from them. And so we can measure that numerically by taking a ratio of the scale that we measure on the map to the expected scale. So for example, let's say we have a map with the intended reference scale of 1 to 235,043,988. So this means that every unit on our map should represent 235,043,988 units in the real world. This is our reference scale. This is what we expect everything on the map to be. Right? But we measure on our map a line, and we find out that the distance is actually at a scale of 1 to 222,660,646. Right, this is the measured scale. Right? This is what we actually have on the map after we've gone through the process of projecting. Right? The scale factor would just be the ratio of this to this. So if we do the scale factor, right, that would just be 2, 2, 2, 6, 6, 0, 6, 4, 6, over 2, 3, 5, 0, 4, 3, 9, 8, 8. And if you do that division, you end up with 1.056. Right. So all I did was I know the scale that I wanted, I got the scale that I measured, I did the ratio, and I got a result. But what does this result mean? Right, what does this number mean? Well, it's greater than 1, which means that we are actually making the objects larger than they should be. All right, so an SF greater than 1 means objects are larger. An SF equal to 1 means that we actually have our intended reference scale. Objects are at reference scale. And if we have an SF of less than 1, then that means that we've actually shrunk our objects. It means that objects are smaller, right? So hopefully that makes sense. We can compare what we're actually measuring on the ground to what we were supposed to get based on the reference scale of our intended globe. Take the ratio of that, and we get some value. The closer it is to 1, the closer we are to being accurate. The larger, the bigger the objects, the smaller the objects, relative to what we would have expected. So that's sort of the mathematical approach that we can take. The other approach that we can take is visually. We can visually examine distortion. And we do this through what's called the Tissot's indicatrix. And essentially, you can think of Tissot's indicatrix as being the way that a circle changes as we go away from those tangent or secant lines. And you can imagine 2 cases occurring, well, 3 cases, right? There's 3 possible cases. So we have our circle, our standard area circle at the reference scale. And there's 3 cases. Case 1, we make the circle larger, but it preserves its shape. Right, the circle maintains shape, but changes area. Right, this means that we're addressing this idea of angular distortion, but we're allowing areal distortion. That's the first case. The second case is where the circle maintains its area, but it changes its shape. So this would be where your circle becomes an ellipse. So these, if you see this pattern happening, where you're preserving area but changing shape, this means that you've addressed this area distortion at the cost of the shape distortion. And again, you cannot have both of these. You can either have one or the other. You either preserve the angles or you preserve the shape. There's no real way to do both perfectly. And then finally, you have something where you change both area and shape. You change both area and shape. So this typically would be more indicative of what's called a compromise projection, where you know you're not going to be able to have both, so you make a compromise so that you have a little bit of error in both area and shape, rather than preserving one at the cost of the other. So that's Tissot's indicatrix. So again, that's the 4 types of distortion. We can have shapes and angles being distorted. We can distort the area, direction, or distance. And we can sort of examine that distortion through 2 ways. Numerically, with a scale factor, which is just the ratio between what we would have expected to have versus what we actually have at a given location. And we end up with a number where 1 means we're perfect, larger than 1 means we've exaggerated, and less than 1 means we've compressed. Or we can use Tissot's indicatrixes, which are just the circles, and you can examine how they change in terms of area and shape as you move across the mapped area. So hopefully this all makes sense, and if you have any questions, as always, please reach out. Thank you.